Now that we have the theoretical background under our belts, we are in a position where we can start talking about more of the practical aspects of atoms and how these various energy levels play out and what do atoms do. One of the things that atoms do is they absorb and they emit. And again, this is going to be a familiar concept to you. So you know that you have a positive nucleus and that you may or may not have all these energy levels that surround an atom, right? You know, you have your n equals 1, so n equals 1, n equals 2, n equals 3. And let's suppose that we send some light over here to this atom, a little photon, right? We send a photon. And, you know, that photon has a certain amount of energy. And let's say that we have an electron that's, you know, doing its little orbital thing right here around. Remember, this is a visual approximation. Really, the electron's smeared all over that space, but we're going to think of it as an electron just moving around at that Bohr radius. So that photon goes into this atom, you know, there's really no choice but for that electron to absorb that energy. And that electron absorbs that energy. If this photon is just the right amount of energy, let's say the difference between the n equals 3 and n equals 1 energy states, then that electron's like, woo! And it jumps up there, right? But these higher level orbitals, right, just like a ball resting on top of a hill, it's unstable, right? Eventually, small little gust of wind, the wind will blow and it will fall. You know, the ball will roll down the hill. Same thing with the electron. After a while, this electron is going to go back to the ground state, right? That's what things do. They roll down, right? But in so doing, it's given away a certain amount of energy, all right? Now, what kind of energy? Well, the same amount of energy as the photon that got excited up there to begin with, right? So that means that in the process of falling back down, you're going to have another photon of the same exact wavelength. So this is some wavelength lambda. Same wavelength lambda is going to be emitted. So this is the process of absorption and emission. Here is an absorbed photon. And remember, there's only certain frequencies it can absorb, and those frequencies are the frequencies that involve the exact energy. So remember, this has an energy of hc over lambda, or h times frequency. Planck's constant is h. So the only wavelengths of light it's allowed to absorb are the ones in which it has energy that's exactly the difference between certain orbitals. Either 1 and 2 could be, you know, 3 to 2, could be 5 to 1, right? It'll absorb only those frequencies such that the energy between the energy levels are precise energy differences between orbitals inside that atom. And this set of frequencies is called the absorption spectrum, okay? We'll talk more about that in a little bit, but for every single element, there are unique energy levels. And those unique energy levels means there's a unique set of wavelengths that are allowed to be absorbed, and those unique set of wavelengths are called the absorption spectrum. Okay, now, here's the thing. We're going to look at the energy levels for a classic hydrogen atom. And this picture here shows it, but I'll write it here anyways. We have n equals 1, n equals 2, n equals 3, n equals 4. And, you know, we have various energy levels that are associated with these different orbitals. And this energy level here is equal to negative 13.6 electron volts. This energy level here, we'll call this E1, this is E2. This one is equal to negative 3.4 EV, and E3 is equal to negative 1.51 eV, and E4 is equal to negative 0.85 eV. And so the energy that is absorbed or emitted for any of these is given by this delta E here, this change in energies between whatever orbitals we're talking about. And so that's going to be HF, which equals HC over lambda. So any lambda that gives you an energy that's precisely the difference between one of these two energy levels, that is allowed for a hydrogen atom. So let's take a look at the emission spectrum or absorption spectrum for hydrogen, and you'll see that there's these different colors that are associated with different changes in energy. So I am going to go ahead and prove to you that for example, jump from the n equals 3 to the n equals 2 orbital is going to give me red light as this picture suggests. So you can see in this picture that there is red light, this arrow is red from the n equals 3 to the n equals 2 jump. So from here to here, it appears to be red light. Let's prove that. Okay, so first things first, remember this relationship has to be obeyed. The change in energy between these two levels, so in other words, E3 minus E2, and we could just take the absolute value. We want change in energy between those two states. That change in energy must equal HC over lambda. Okay, now the change in energy between these two states is, negative 1.51 minus negative 3.4 eV equals HC over lambda, right? Now, so the difference between this is actually 1.9 electron volts. But remember, this here is all represented in SI units, so we need to convert this to joules really quick so that, things work out. So remember, there is 1.6 times 10 to the minus 19 joules for every electron volt, okay, equals HC over lambda. Remember that H is equal to 6.6 times 10 to the minus 34 joules seconds. C is equal to the speed of light, 3 times 10 to the 8 meters per second. And if I put this in here and solve for lambda, which I encourage you to do with me, I get a value of 485 nanometers, right? Or 4.85 times 10 to the minus 7 meters. And if you look that up, you will find, sure enough, that that value is in the red part of the spectrum, okay? Now, very clearly, I have run out of space here. So I am not going to be able to prove this yellow, green, blue, and violet, but I encourage you as an additional part of your homework, in order to get comfortable with this here relationship, right? This is the relationship, and this is important to be able to calculate, and you will be required to do it for an exam. So, wink, wink. Now, being able to use this relationship where the difference in energy between two orbitals is going to correspond with one specific wavelength or frequency, be able to prove that. And so I encourage you to practice proving that the drop from energy level 6 to 2 gives you something in the violet spectrum, from 5 to 2 gives you something in the blue spectrum, from 4 to 2 gives you something in the green spectrum, etc. So practice that, see if you're getting values in that general region, and get comfortable using this relationship.